So this is the next question of Code Chef Starter 114, game on array. So in this question, you're given an array of size n, and the constraints of n are from 1 till 10 power 5. And the array values can be from 1 till 10 power 9. And the number of test cases are from 1 till 10 power 4. And sum of n overall test cases does not exceed 10 power 5. Okay. So in this question, you're given an array. Let's say the array is 3, 1, 2. Okay. Now, in every operation, in one move, now two people are playing a game, Alice and Bob. Okay. So the move Alice makes is he'll pick up two elements with same parity. Okay. Two elements like two indices, let's say I and J. Okay. And they both have the same parity. Okay. Now this I and J can be the same value as well. So basically he can pick up I and J as the same value as well, or he can pick as different values as well, up to him. But if he picks up different values, then they should have the same parity, which means either both of them should be odd or both of them should be even. And what Alice does is he removes one, he decrements that number by one, both of them by one. Okay. So let's say he picks up 3 and 1. He can decrease both of them by 1, which will result in this becoming 2, this becoming 0. Okay. And also the condition is the value here must not be less than 0. It must not be less than 1 because he'll have to remove at least one integer from that, right? So basically, this numbers represent the number of stones. So he cannot remove more stones if there are 0 stones left, right?
So if he picks same indices, he should remove 2 stones.
Right. If he picks up I and J as same indices, then he'll have to remove 2 stones from the same pile, right? So in this case, if he picks up 3, after removing 2, it will become 1. Okay. This is the move that Alice will perform. And now let's see what Bob can perform. Bob also can pick up 2 indices, I and J. But in this case, both the indices must have a different parity. Different parity. And what Alice does is, he'll take one stone out of pile I and place it in the pile J, right? And since he's removing one stone from here, this pile must have at least one stone, and this pile can have 0 or any number of stones. It doesn't matter because we are placing one stone on that pile. But the main condition is both of them should be of different parity. And they cannot be same because the same pile cannot have different parity of stones. So I and J have to be different in this case. So now Alice and Bob are playing this game starting from Alice, and they keep playing this game until some player is not able to make a move. So let's say Alice cannot find 2 elements with the same parity. So Alice loses the game because he's not able to make a move. Or in any case, Bob is not able to find 2 piles with different parity number of stones. Then Bob loses the game. So yeah, this is how the question is. So in this test case, let's say Alice makes a move. He removes 3, 1 from here and 1 from this, and that's the only move he can make. She can make. So it will be 2, 0. Okay. Now Bob cannot make a move in this case, right?
He can pick last one and this. Their parities will be different.
This and this. No, this has even parity and this is odd parity, right? I mean, both of them have even. So there's a small correction here. Basically, we need different parity for the indices. So this is 0, 1, 2, right? So basically this element and this element, this index and this index have the same parity. So this becomes 2, 1, and 1. Okay. Now Bob will have to pick up one of this index and either of these two, right? So let's say Bob removes one element from here and adds one here. Then the array will become 2, 0. Okay. Now it's Alice's turn. He'll remove one element from here and one from here. So basically it becomes 1, 0, 1. Right? He picks up these two indices. And now it's Bob's turn. So Bob will pick up this is I and this is J and move one element here. So that will make it 0, 1, 1. Okay. Now Alice is unable to make a move because the only two elements he can pick up is this and this, and both have different parity. So yeah, it's not possible for him to make a move at this point. Now in this situation, if Alice had picked up this element only as I and J both and removed both elements from here, that would result in 0, 0, 2, and Bob would transfer one element from here to here, and Bob can still win the game afterwards. So in any situation, it's not possible for Alice to win this game.
So in this, we can do case work. Firstly, let's handle an obvious case, which could be edge case in the future. So when n is 1, if n is 1, we only have one index, right? So that means in n we have some value. Let's say we have x. Now first, Alice will for sure perform operation. So if n is 1 and this x value is 1, then Alice can for sure not, because he's playing first. In this scenario, answer is Bob. And if x is greater than 1, Alice can win, right? Because Alice can perform at least one move. And now it's Bob's turn, and Bob don't have any index to transfer.
Exactly.
So in the case of Alice, he can pick the same index twice. So that's why he can perform at least one move.
Right.
So if n is 1 and this holds, then for sure we know this is how the game works, no? If they play optimally.
Right, exactly.
Now if n is greater than 1, now let's say if n is greater than 1, there are two scenarios. Firstly, let S be the sum of all the elements present. If S is a odd, then the claim is for sure Bob will win. Why? Because let's say we have some elements in this. Now, in Alice move, if he observes, he'll always remove two elements. So that means sum will always reduce by 2. So for sure, at a point, because S is odd, there will be at least one value which couldn't be paired with any other value in Alice too. But Bob, in the case of Bob, let's say we know the final configuration, how it looks. Final configuration can look like we'll have one somewhere, anywhere we can have. It doesn't matter where we have that, and rest all can become 0, because Alice will ensure they'll become 0.
Right.
So this one, Bob can in Bob's turn he can move it to anything, because n is greater than 1, there exists at least one thing with there'll exist at least one pair with different parity.
Right.
As n is at least 2. So now in this scenario, because this one Bob can move anywhere, but Alice can never remove it, we can say Bob will win in this scenario. Now, the only scenario that we have left is when n is even. When n is even, let's analyze who will win.
Okay.
So when n is even, when can Alice lose?
When there are all the elements, no, when there are only two elements left, and both of them are of different values. Right.
So can we say that because Alice is always removing 2, so for sure he'll remove even things from this one, right? So finally, if we are left with 1 and a 1, basically a 1 in a 1 in even index and a 1 in odd index, then Alice can't perform again.
Exactly.
Whereas if we are left with a 1 in even and 1 in even again, then he can perform and Bob will lose.
Right. Yeah.
So we should detect with what end state will the game terminate. So for that, let's analyze one thing. We can analyze something like this. That is, if we have S as our sum, we can observe that for sure, Alice will always reduce the sum by 2 minus 2.
Right. Yeah.
No matter what, he'll always reduce the sum by 2. And we know terminating states will have a sum exactly equal to 2 when S is even.
Right. Yeah.
And S can never be 0 because values are at least 1. So, because terminating state will have at least 2, and Alice can remove 2 in every move.
Right.
So, in total number of rounds that we'll be playing is S minus 2 by 2. Right? These many rounds of games with Alice and Bob both will play.
Right. Yeah.
And now, if we look over, what happens here is, let's say in evens and odds, let the even sum be something and odd sum be something. And initially, if even sum is an even number, then for sure odd sum will be even number.
Right.
Because S is even.
Right. Exactly.
Similarly, if even sum is odd sum will be odd. These are the two states with which our game can start up.
Exactly.
So if even sum is even and odd sum is even, then what happens is at round 0, the configuration looks like even, right? Whenever at round 0, that is when no move is played. For even, the sum is even. For odd, the sum is odd. The sum is even. Right?
Exactly.
So after playing one move, what happens is, because of Alice, parities won't affect.
Yeah.
Right? Because he's removing 2, so he'll either remove even from evens or even from odds. So evens and odds parity will differ.
Yeah.
But after Alice play, so here it remains even. This is when Alice is playing. Now, in the second turn, which is Bob's, these will flip if we observe. Because for sure he'll be moving one from even to order or to even.
Exactly. Right.
That means because parities were even, now it became order. Now in the third turn, again it remains the same.
Yeah.
Right? Because Alice can't change anything. Now in Bob's turn it will become even. So if you observe, these parities are just getting flipped each and every time. So that means
at every Bob's turn,
it gets flipped.
Right.
So now, finally, when we are at the terminating state, we should have both evens and odds parity as even. Then only Alice can. Right?
Both even and odd parity as even.
Because terminating state will occur when there are only 2 elements.
Right.
So when there are 2 elements and even positions parity is even, odd positions parity is odd positions parity is even, that implies that those 2 elements which are present, they are either in evens or either in odds.
Okay. So basically, both the elements are present in same element.
Same element.
Right. So in that case, Alice should be.
Yeah, Alice should be.
Okay.
So when the parities are even, then only he can win. Because if both are present in evens or odds, then both parity will be even.
Right.
So now we just saw after every Bob's turn, the parity is getting flipped. So if we look over this, if initially the parity was even, we can check this.
Okay.
If it's even or even,
right.
By calculating even sum and odd sum.
Right.
If even sum and odd sum are even, and we know how many rounds will Alice play before terminating.
Okay.
So number of rounds that both of them will play before terminating would be S minus 2 by 2. Right?
Right.
These many rounds they both will play. Now if S minus 2 by 2, and we know what is the parity. So if it is even, then
at the end also it will be even.
At the end also it will be even.
I mean, okay.
It depends on the parity.
It depends on this value, right?
Yeah, it depends on what the parity of this is.
Right.
So let's say if this both of them started with even. Then for Alice to win, how this should be even or odd. Let us just check that. So here we are performing. Initially we started with events. Right? Yeah, initially we started with events.
Right.
Now we are playing two complete games. That is, this is one complete game where Alice and Bob both play.
Right.
And this is one more complete game where Alice and Bob both play.
Right.
Now, if this is even and the parity of s minus 2 by 2 is also even. So here if we see s minus 2 by 2 will be, let's say there are 6 terms. Basically, let's say this is the terminating state.
Right.
Fifth term is the terminating state. Then s minus 2 by 2 should be even, right?
Yeah.
Because after 2 turns, it will flip back to evens.
Right.
So if this is even, this should also be even. Then Alice can win. And if similarly, if this is odd, this should also be odd. Because same thing holds.
Right, yeah.
So let's just check for odd. If this is odd and odd, then this becomes even, this becomes odd, odd. This will remain even. In Bob's turn, it will flip to even. Then
it will remain even.
It will remain even. Now here it becomes odd, odd.
Yeah.
So if this parity is even, then we are ending at odd, odd, and it will be Alice turn.
Yeah.
But if the parity is like if this one's parity is odd, that is when we are over here, we can see we had even. So in the next turn, Alice can remove those two values which were which were present. So if the parity, if the initial parity, that is basically if evens and odds are even, we can just check for one of them because other thing will be symmetric. So if sum of even numbers is an even number, then number of rounds played should be even. Then Alice can win. And if sum of even numbers is an odd, sum of even numbers is an odd number, then number of rounds played by them should be odd.
Right.
Then Alice can win. In other cases, Bob will.
Okay.
Otherwise Bob. If this holds, it's Bob. So if we look at the time complexity of this would be big of n, right? Because we just compute sum of events and totals.
Exactly, right. Yeah.
And rest all is just order of one operations, checking in if condition.
Right, exactly.
So that's why time complexity is O(n) and space is O(1) as we just used to.
Right. Yeah, I think this is clear.